Hello, my name is Bill Robbins. In this video I'm going to talk about diodes for power electronic applications. Before I begin, I strongly urge you to have already viewed the video on review of basic semiconductor physics, because this discussion on diodes is going to be based on that background. In this video I'm going to talk about the following topics: the basic construction of a power p-n junction diode, what determines their breakdown voltages, then on-state losses, switching characteristics, then a brief discussion of Schottky diodes, and finally a brief discussion of junction barrier Schottky diodes, sometimes termed JBS diodes. The next slide shows the basic construction of a p-n junction diode for power applications. Its distinguishing feature is the vertical current flow from the top surface where the anode is to the bottom surface of the wafer where the cathode is located. Signal level diodes have both the anode and cathode on the top side of the wafer, and current flows parallel to that top surface in a horizontal direction. The reason for the vertical orientation is it gives us a much larger cross-sectional area for current flow, so we can have very large currents flowing in the power diode without excessively high current densities. There are three layers to the power diode: P plus anode region, which is very heavily doped; a more lightly doped epitaxial region, which is often called the drift region, and the thickness of this drift region, which I'm illustrating right here, is dependent on the breakdown voltage requirement. And finally, we have a very heavily doped N plus substrate, which the cathode is connected to. The IV characteristic of a power diode is very similar to that of a signal level diode, the main difference being the scaling of the current and voltage axis. In the forward direction at low currents, we have an exponential relationship between the current and voltage, but at modest currents and as we go to larger currents, the current becomes proportional to the voltage, and the slope of that linear region is 1 over the on-state resistance. In the reverse direction, no current flows until we reach the breakdown voltage due to impact ionization, and the breakdown voltage rating of power diodes can range from a few tens of volts to several thousand volts, depending on the application. The circuit symbol for a power diode is identical to that for a signal level diode. The first characteristic, and probably the most important for a p-n junction diode for power electronic applications, is its breakdown voltage. And the following considerations determine what the breakdown voltage rating is. I'll first consider what is called a non-punch-through geometry, which means the width or thickness, if you like, of the drift region is at least equal to, and usually somewhat greater than, the width of the depletion region at the rated breakdown voltage. Based on the review of basic semiconductor properties we went through, we know that we can write the width of the space charge region by this formula, and similarly the thermal equilibrium value of the space charge region is given by the formula I just highlighted. And the maximum electric field is, as a function of the reverse voltage, is given by this formula. These formulas simplify in practical situations. For a power diode, we usually have the acceptor density much larger than the donor density in the drift region, and at the rated electric field, that's the breakdown field strength, E sub BD, and at the rated voltage we designate that voltage as EV with a subscript BD. Under those circumstances, there is a simplified form of the width of the space charge region and of the value of the space charge region at zero bias or thermal equilibrium. Going to the right hand side, if we solve for the breakdown value of the depletion layer thickness and the breakdown voltage and put in numbers as much as we can that apply only to silicon, we can show that the breakdown voltage is proportional to 10 to the 17th divided by the donor density in the epi layer. The width of the depletion layer at breakdown is equal to twice the breakdown voltage divided by the breakdown field strength, and that can be shown to be equal in microns to about 10 to the minus 5 times the rated breakdown voltage. The conclusion we come to from these considerations is large breakdown voltages, for example 1000 volts, will require a donor density in the epi layer of 10 to the 15th or less. And simultaneously, it requires that the length of the drift region be on the order of 100 microns. So high voltage devices are going to have relatively thick drift regions and relatively light doping densities in the drift region. However, there's more to the breakdown voltage considerations than just the values that we estimate for an ideal geometry. First of all, the non-punch-through geometry is not the only geometry that we may be using. There is another one which is called the punch-through structure, which is illustrated in this slide. By punch-through, we mean the width of the drift region, W sub D, is less than the thickness of the depletion layer at the desired breakdown voltage. As a consequence of that, our electric field profile is no longer just triangular shaped. It has two contributions that I've illustrated here. One is a value E2, in which we have a spatially uniform electric field, and then a triangular shaped portion to the electric field, which I've designated as E1. The sum of E1 plus E2 at the P plus and minus interface is the maximum electric field, and the voltages that correspond to E1 and E2 are designated here in the drawing. And it's easy to show that E1 is given by this formula, and V1 is given by this, and V2 is equal to E2 times W sub D. At breakdown, we set the sum of V1 plus V2 equal to the breakdown voltage. The sum of the two electric field contributions we set equal to the breakdown field strength. And solving these equations, the breakdown voltage for a punch-through device is given by the equation I've just circled. And if we have a low doping density, N sub D much less than this factor right here, which is the value that is required for a non-punch-through diode, then we have the breakdown voltage is roughly equal to the breakdown field strength times the depletion layer thickness, and the width W sub D of the drift region is about half of that for the same breakdown voltage if we were using a non-punch-through structure. For diodes, probably the punch-through structure doesn't have any significant advantages. However, there are blocking junctions in some of our other devices that we'll be considering, particularly the IGBT, which having a punch-through structure is an advantage. And in fact, we have punch-through IGBTs and non-punch-through IGBTs, and we'll be talking about those in a separate module. Continuing on, the other factors that influence our breakdown voltage is any curvature that may come about in the space charge layer boundary. The p-n junctions that we formed are normally formed by diffusion, and the result of the diffusion process, which I've highlighted here, results in the metallurgical boundary having a radius of curvature, particularly outside of the area where the window was opened in the masking of the diffusions in the process of fabricating the p-n junction. As a result, when we reverse bias this p-n junction, we have the same type of curvature in the depletion region. Here in the plane parallel section that I've outlined here, we would estimate the breakdown voltage on the considerations that we just highlighted. However, the actual breakdown voltage is going to be less than that because there are field crowding problems here where the radius of curvature is fairly small. In fact, this field crowding problem is exactly the same as what we have in a coaxial cable, where the field at the center conductor is significantly larger than the field at the outer conductor. And because of this, our achievable breakdown voltage may be significantly less than what we estimate on the basis of this plane parallel section that I've encircled here. It can be shown that on the basis of modeling a cylindrical p-n junction, that the radius of that junction has to be 6 times the desired thickness of the depletion layer at the rated breakdown voltage in order to limit the breakdown voltage reduction to less than 10%. In other words, keeping 90% or more of the plane parallel estimate. For radiuses of curvature that are less than 6 times that, we have a significant reduction in the breakdown voltage. Another consideration is that it's probably going to be impractical to have such diffusions that are 6 times larger than the desired width of the space charge layer. For a 1,000 volt breakdown, we need something on the order of 100 microns for the depletion layer. 6 times that is 600 microns. It's going to be nearly impossible to make a diffusion as deep as 600 microns. So we want to have some other method of reducing the effect of the field crowding. And that's where we use techniques to control the space charge layer boundary contour. Instead of allowing the p-n junction, the depletion layer boundary, to do this kind of thing that I've highlighted here, we use field plates or guard rings to force the depletion layer to have a much more gradual change in its shape. In other words, a much larger radius of curvature. We achieve this either by so-called field plates, which are open circuited pieces of thin film metallization placed strategically so that as they operate as an equipotential surface, they force the boundary of the depletion layer, which is also an equipotential surface, to conform to the appropriate shape so that we do not have field crowding problems. Here we can also do essentially the same thing with extra p-type diffusions, which we call guard rings, because the p-type region is heavily enough doped that it also functions as an equipotential surface. And in very large devices, which are made to handle large currents and large voltages, often the entire wafer is used for the device. And in those circumstances, we have to worry about the edges, the vertical edges that I'm highlighting here, and what their influence on the breakdown voltage might be. Because as I'm indicating in this drawing, there are field crowding may occur at the edges of the wafer, and so that may require special contouring of the wafer and even surface passivation, which means on the surface of that contour that we've put in, we also put a dielectric like SiO2 to further passivate the layer and prevent the fringing fields from reaching out into free space. As a user of these devices, you're not necessarily going to be having to worry about the details of how to implement these factors or ways of increasing the breakdown voltage, but you need to be aware of them so you can appreciate what the device designer has to do and the person and the company that's fabricating these devices. The next thing we have to ask is, what happens when we turn on one of these devices? We already know that the current is going to have to go through the drift region, and we purposely have to have a fairly lightly doped region to have a high breakdown voltage. Well, light doping implies a fairly high resistance in this drift region. So the question is, won't the losses in our device, the ohmic losses, be so high that we will burn the devices out? The answer would be yes, except for the fact that we can make use of a mechanism called conductivity modulation of the drift region. You'll recall that a forward bias p-n junction means that we are going to be injecting excess carriers across that metallurgical junction. Holes from the p-type region into the drift region, and from the n+ region will inject electrons into the drift region, so-called double injection. If we make the diffusion lengths of these excess carriers at least the same magnitude as the drift region length, it will be possible to achieve a fairly spatially uniform excess carrier density that I've indicated right here. And that excess carrier density on average can be orders of magnitude larger than the thermal equilibrium value. In this particular drawing, I've illustrated that the electron density in the drift region, N sub n naught, is about 10 to the 14th. That low in order to support 1,000 volts or more in reverse bias. I'm talking 10 to the 16th, possibly 10 to the 17th excess carrier density. So in the forward bias region, it's possible that we can have enough excess carriers that we can lower the on-state resistance from its ohmic value down to a value of about 1/1000th or even smaller of the ohmic region value. And in this way, we can then greatly reduce the on-state losses. Well, we need to be a little bit more quantitative than just making the statement we're going to reduce the on-state losses. We want to be able to calculate roughly what those are. And we can do it in the following way. We know that we have an excess carrier density in the drift region. And because of recombination mechanisms, we know that the total stored charge in the drift region is going to be decaying exponentially if we don't replenish the recombining carriers. And so in a steady state non-equilibrium situation where we have a constant forward current, the forward current simply replaces those devices or those charges that disappear because of recombination. So I sub f is basically Q sub f over tau, and that can be made more explicit if we know the average density of the excess carriers N sub A times WD is the volume, and I know the lifetime. We can write the forward current in terms of this stored charge formalism. Now, when we talked about a stored charge formalism in the case of the simple PN junction, we were talking about currents flowing by diffusion because of the steep density gradients right near the metallurgical junction. However, we have a carrier distribution in the drift region. First of all, in the center of the drift region, we're a substantial distance away from the metallurgical junction, and secondly, the distribution is quite flat. So current cannot be flowing by diffusion. It is in fact flowing by drift. So if we take the same current and write it in an Ohm's law format, we get this equation right here. If I divide the forward current by the area A, I get the current density, J. If I solve the equation I've just highlighted for the drift region voltage drop, V sub D, I have a voltage drop given by this equation, and it's independent of the forward current. In fact, it appears we could make that drift region voltage arbitrarily small by having very large values of carrier lifetime. Well, we already know that we do not want to have excessively large values of carrier lifetime because it would greatly slow down the switching speed of the device. And even if we don't have a very large, infinitely large value of carrier lifetime, it's unrealistic to expect that we're going to have the drift region voltage independent of the current. So we need to look at this in a little bit more detail. The next slide does this. We can estimate the voltage drop across the drift region in the following way. The mobilities are not constant. Their low-level values, mu naught, are the sum of mu n plus mu p at low doping levels, 10 to the 14th or so. But from an empirical viewpoint, we know that the mobilities decrease as we increase the excess carrier density or we increase the doping levels. The empirical formula is that mu becomes inversely proportional to the excess carrier densities when the excess carrier densities reach a value on the order of 10 to the 15th to 10 to the 16th. If we put that density-dependent mobility into our equation for the forward current and the drift region voltage, this is the equation that results. The reason for the mobility reduction is due to increased carrier-carrier scattering. That is, at 10 to the 16th and higher, the electrons begin to scatter off of each other because of Coulomb repulsion, and this is the reason for the drop in the mobilities. If we assume that our excess carrier density is as large or larger than about 10 to the 16th, then an asymptotic expression can be developed in which we ignore the 1 compared to NA over N sub B, and then invert that relationship and show that the drift region voltage is proportional to the forward current, and all of the other constants that I'm highlighting right now constitute the on-state resistance. The total voltage across the device is given by this expression. It's the drift region drop plus the junction drop being on the order of 0.8, 0.9 volts, depending on what the current level is. How large can V sub D be? That's going to be a function of how much power dissipation you can tolerate in the on-state. Typically 2 to 3 volts is the maximum that is normally found across a diode used in power electronic applications. So far we have discussed breakdown voltage and on-state losses. We also have to consider the switching characteristics of these p-n junction diodes, and that's what this next slide discusses. I show two waveforms, current versus time and the voltage versus time. In the current, at t is equal to 0, we begin to turn the current on at a rate of dIf by dt. That ramp rate for increasing the forward current is dictated by the external circuit, either a series inductance and a power supply voltage, or the speed of a switch, which is in series with the diode. So it takes a time t1 for the current to ramp up to the forward on-state value. It then is maintained in the on-state for the desired period of time, and then it begins to turn off. The diode turns off, the diode current turns off at a fixed rate dir by dt, again set by the external circuit. It goes from the maximum forward value down to 0 in a time t3, and then goes from 0 to a maximum negative value in a time t4. That maximum negative value is the so-called reverse recovery current I sub RR. And then from the peak negative value down to some value, either 25% of the peak negative current or 10%, whatever seems reasonable to you, takes a time t5. Corresponding to the times in which we were looking at the current, there's also the voltage that we need to look at. T less than 0, we have the reverse bias voltage on the diode. As soon as the current begins to ramp up, the voltage goes from this negative value, ramps very quickly to fairly large positive values, can be as large as a few tens of volts. So there's a voltage overshoot that occurs in the time t1. When the current reaches its on-state value, that voltage then drops down from the peak forward recovery voltage down to the on-state value in a time t3 that we have, or t2 that we have already talked about. I guess I was talking t1 here, and here is t2. It remains at that on-state value of 2 or 3, possibly 4 volts during the rest of the on-state interval. Then when the current begins to shut down, the voltage still remains positive and roughly at the on-state value, dropping only a little bit, but still positive. Even when the voltage or the current goes negative, we still have a forward voltage on the device. The voltage does not start to go negative until the point where the current goes to 0 and begins to have its steepest slope during the transition towards 0. At that point, the voltage very quickly goes negative. It reaches a peak negative value that we can call V sub RR.
and then as the diode current dies out, the voltage decays down to the reverse bias value. A couple of questions we need to answer is, what causes this kind of behavior? And secondly, what does it imply in terms of how we make use of the diodes? Well, let's take it interval by interval. During the turn-on interval, T1, here is a picture of the device in a simple one-dimensional horizontal orientation. And the equivalent circuit is a space charge capacitance, drift region resistance, and possibly some inductance due to stray inductance, and the wiring of from the diode to the outside world. Space charge capacitance is usually modeled as a capacitance where the distance between the plates is equal to the space charge width, and on one plate you have the total positive charge in the positive space charge part of the depletion region, and the total negative charge on the negative plate is the negative charge in the negative side of the depletion layer. The drift region resistance starts off at the ohmic value during turn-on before you have any stored charge, and gradually gets reduced down to much lower values as you achieve the steady state non-equilibrium value of excess carriers in the drift region. During the initial T1 interval, where we don't have much in the way of stored charge, as the current grows, we have an ohmic resistance, so increase in current means we're going to have an increase in voltage. And because the currents may be fairly large and the resistance large enough, that is going to contribute to the overvoltage that we have shown earlier. The other thing that may increase that overvoltage is as we ramp the current up, any stray inductance will give us a contribution to the voltage of L times di dt. So your forward peak voltage is the forward current times the ohmic resistance plus L times di dt. During the T2 interval, the current now through the device is constant. Any contribution of the diode voltage from the inductance is now gone, and now the resistance is beginning to decrease because we are filling up the drift region with excess carriers. And I'm showing in a qualitative manner the growth of the excess carriers as a function of time. And when we achieve the value of after the time interval T2, we have a steady state and fairly flat distribution, and we've reduced that resistance by several orders of magnitude, so that now we have the on-state that current times the effective on-state resistance now gives us the 2 or 3 volt drop across the drift region that we anticipate. During diode turnoff, we essentially have the opposite behavior. We have to get rid of the excess carriers, so that means that we have a picture of the excess carriers decaying as I'm showing here, starting from the flat distribution at t is equal to 0 and gradually removing those excess carriers by a combination of one internal recombination, and also due to what we call carrier sweep out, that is the negative current carrying a lot of the stored charge away. So that means we're changing the charge on the capacitor, and because of the inductance we have an L times a di dt, and during that time interval T5, where we can have some very steep changes in current in relatively short periods of time, that L times di dt can give us over voltages which may approach or even exceed the breakdown voltage of the diode. And so in that case, where we may exceed the breakdown rating of the diode, we're going to have to do something. That could be either in the form of using diodes that have higher ratings, and secondly have a softer switching characteristic, not so abrupt. In other words, the time T5 is larger, or we may have to put in special circuit components to implement what we call a snubber to prevent the voltage from being so large. Now, if I go back for a moment to the first picture, you'll notice in the interval T4 plus T5, I have defined the area under the current curve as Q sub RR. That's the total area under the current curve during the reverse recovery time, and we approximate it as a triangular shape so that Q sub RR is I sub RR, T sub RR divided by 2. We can make use of this to make some quantitative statements about what factors determine the reverse recovery time and current. From that picture, it's easy to write, or easy to see that I sub RR is dir by dt times the time t4. That's usually rewritten in terms of T sub RR over S plus 1, where S is the so-called snappiness factor, and again, S is equal to T5 over T4. So if you have a very short turnoff, a very so-called snappy turnoff, T5 is quite small, and you're going to get very large rates of change of current, and hence any inductance is going to probably give you a significant overvoltage. We can also write an expression for Q sub RR, as I've done here. And if I invert those two equations and solve for T sub RR and I sub RR, I can get this expression for T sub RR and this expression for I sub RR. There's really no physics involved here, it's just the definitions that we have used on these waveforms, but they're significant in the following way. T sub RR depends on 1 over the square root of the dir by dt. So if you want short recovery times, you need to have very large dir by dt. Unfortunately, the reverse recovery current scales as a square root of dir by dt. So there's going to have to be a trade-off made between the desired T sub RR and I sub RR. And that is the trade-off that the diode user has to make. We can also get more useful quantitative information by recognizing that if we have a fairly short reverse recovery time, shorter, say, than the carrier lifetime, then most of the carriers in Q sub RR are going to be removed by carrier sweep out. That means that we don't lose many by recombination, so it's fair to equate Q sub RR to the forward stored charge, Q sub F, which is equal to the forward current times the carrier lifetime. Using this relationship in the equations that I've already talked about for I sub RR and T sub RR, we get this equation for the reverse recovery current and this equation for the reverse recovery time. And you'll notice that the larger I sub F is, everything else being constant, you're going to have a longer reverse recovery time. And similarly, the larger the forward current, the larger the reverse recovery current is going to be, everything else remaining constant. These equations can be made even more useful to illustrate the carrier lifetime breakdown voltage trade-offs that have to be made by the device manufacturer. Low on-state losses require that the diffusion length be at least equal to the width of the depletion layer at breakdown voltage. So that means you want the diffusion length L to be equal to the drift region length, which has to be at least equal to, if not a little bit larger than the depletion layer width at breakdown. So setting the diffusion length equal to the depletion layer thickness at breakdown and solving for the carrier lifetime gives the following. The carrier lifetime is given by symbolically by this equation, and when you put numbers for silicon in, it is equal to 4 times 10 to the minus 12 times the square of the breakdown voltage. I can substitute this expression for carrier lifetime into the equations for T sub RR and I sub RR, and these are the results. T sub RR gets larger as it's linearly proportional to the breakdown voltage that you want, and so is I sub RR, the reverse recovery time. So the conclusions we come to is high breakdown voltages require larger carrier lifetimes to maintain low on-state losses, and that means these devices are going to be slower because of the longer required lifetimes, and the only way we're going to shorten turn-off times is by having large dir by dt, but that means the larger the reverse recovery current slope is, the greater the value of the reverse recovery time. So there's some trade-offs that you as the user are going to have to make. Fortunately, for some applications, there's a different kind of diode that we can use, which has some advantages over the p-n junction diode. These are the so-called Schottky diodes. The basic structure for a Schottky diode is a two-layer structure. Moderately doped N region, which functions as a drift region, and the N plus substrate, the drift region being this entire space right here. Its thickness is going to be dictated by breakdown voltage considerations. There is no p-n junction. There is a depletion layer which is formed up near the anode, where we have a metal moderately doped n-type silicon interface. And if that metal is aluminum or aluminum with some dopants, that forms a rectifying contact, and I'll get into why that may form a rectifying contact in just a moment. The other thing that we absolutely must have is guard rings, because at this interface we're going to have a depletion region, because the doping in the drift region now has got to be significantly higher than it is in the drift region of a p-n junction diode. Our breakdown voltage is going to be much less. We're going to have a much thinner, even in thermal equilibrium, depletion layer thickness. That means sharp radiuses of curvature. So we have to have guard rings in order to maintain the estimated breakdown voltage, which we would come to using the plane parallel approximation for the boundary of the depletion region. This device is a majority carrier device. There are no injection of excess carriers, so that means it's going to be a fairly fast device, faster than a comparable p-n junction, because there's no stored charge. However, breakdown voltages, as I've said, are limited to 1 to 200 volts in silicon because of the need to have a more highly doped drift region. It has to be more highly doped because we want to keep the drift region voltage drop to a comparable level as in the p-n junction diode. And without conductivity modulation, we have to have all those carriers brought in by dopants. So typically we would have this doped at several times 10 to the 15th to possibly 10 to the 16th in a Schottky silicon device. Now, as to why there is a why that metallurgical junction forms a rectifying contact, here I've shown in the next slide a simple picture of that interface. Here is aluminum. Here is the n-type silicon. The average free electron energy, that is the conduction electrons, in the n-type silicon have a higher average energy than the electrons in the aluminum. This energy is with respect to an electron in free space a long distance away from the diode. So it takes more energy to pull an electron out of the aluminum than it does the silicon. Because of that, the electrons being more energetic on the n-type silicon side, those that are in the immediate vicinity of the metallurgical junction are going to move over to the aluminum side. Even though there are many more electrons, they're not as energetic, and so there's going to be a depletion layer formed because the electrons in the immediate vicinity from the N-type silicon that moved to the aluminum give us a net negative charge on the aluminum side and a net positive charge from the uncovered donors on the N-type silicon side. All right, we've now formed a depletion region, and so all of the same mechanisms that we were in physics that we were talking about with a p-n junction also apply here. Now, because of the smaller difference in energy between the electrons in the silicon and the aluminum, the contact potential in a Schottky diode is only on the order of 0.3 to 0.5 volts, which is smaller than that in a p-n junction. Hence, the reverse saturation current in a Schottky is significantly larger than that in a p-n junction. The breakdown voltage in a Schottky device can be estimated based on modeling the interface as a step p-n junction, and get the formulas. We can apply the formulas that we use in a p-n junction and find that we're going to have about no more than 100 to 200 volt breakdown rating, because we must have this doping density in the drift region up around 10 to the 16th in order to carry any reasonable sized currents that will be useful in a power electronic application without excessively high voltage drops across that drift region. And of course, we must have guard rings in order to keep that voltage up there based on a plane parallel approximation. As far as the switching characteristics of Schottky diodes, qualitatively they look similar to those of a p-n junction diode. Turn the current on at a fixed rate. There will be some voltage overshoot, primarily because of the inductance that show in the equivalent circuit right here. The resistance is not changing, so the drop that we have from the peak forward voltage down here, this drop right here to here is simply L didt. In the on state, we have the forward voltage, probably on the order of 2 to 3 volts in a Schottky. And then when the device turns off, we turn it off with a fixed externally controlled ramp. It achieves some reverse recovery value and then goes back to zero. And so there's going to be a over voltage in the negative direction, again because of L didt. And we have to make sure that that does not exceed the breakdown rating. Finally, in discussing Schottkys, a question that comes up is, how come we have a rectifying contact at the anode but not at the cathode? Well, it turns out, and I'm not going to get into the details of it, for heavily doped N-type silicon or any doping in P-type silicon, putting an aluminum metal in contact with that material results in what we call an ohmic contact. I don't want to get into a discussion of it, but there's a brief explanation here on the slide. Finally, it's probably worthwhile highlighting the differences, or at least some of the differences, between a Schottky diode and a p-n junction diode. Let's take the p-n junction diode first. That's the equations here on the left-hand side. The minority carrier relationships in the drift region give us this equation for the forward current as a function of the diode voltage and the other circuit and the other diode parameters. We've already derived this equation. Now, the maximum practical value of n sub a might be 10 to the 17th. The corresponding mobilities are about 1,000, the sum of the two. And the desired breakdown voltage requires, as we've already seen, that the drift region length be proportional to 10 to the minus 5, equal to 10 to the minus 5 times the breakdown voltage. Putting all of that information into the equation for the forward current, and then if we divide the forward current by the area, we have this relationship. Bipolar devices, or minority carrier devices, which make use of conductivity modulation, the current density is equal to this numerical factor of about 10 to the 6th times the desired or maximum allowable drift region voltage that you want to have, divided by the breakdown voltage. So all things being equal between the two types of diodes, minority carrier devices have a current density that's inversely proportional to the breakdown voltage. If I go to a majority carrier device like a Schottky diode, here is your equation for the forward current. The breakdown voltage requirement says that the doping density is given by this equation. We know that the width of the depletion region or the drift region has to be given by that. Putting that back into the equation up here for the forward current and putting in silicon values, we get that the forward current is given by this expression for a majority carrier device like a Schottky diode. Almost the same numerical factor. If we assume the same allowable drift region voltage drop, we find then that the forward current for the majority carrier device scales as 1 over the square of the breakdown voltage. The conclusion that we draw from this comparison is minority carrier devices have lower on-state losses at high breakdown voltages compared with majority carrier devices. So as you go to extremely high voltage ratings, you're probably going to be using only p-n junctions. Now, this has been somewhat mitigated in the last few years by the emergence of Schottky diodes made out of silicon carbide, which have breakdown ratings as high as a couple of thousand volts, and in laboratory experiments even larger. I'm going to hold off a comparison between silicon Schottkys and silicon carbide Schottky diodes until later when I talk about wide bandgap devices.
The final topic I want to discuss is the silicon junction barrier Schottky diode, or sometimes termed JBS diode. This slide shows on the left-hand side here a cross-sectional view of a simplified JBS diode. You'll notice that we have alternating combinations of a P plus N junction next to a Schottky diode and then another PN junction. So we have alternating PN junction, Schottky, PN junction, Schottky, PN junction. So we have a highly interdigitated structure. There's no commonly accepted circuit symbol at this point for JBS diodes, and the common practice is to use a standard diode symbol at present. The unique features are the aluminum film, which shorts both the P region and the N-type Schottky region, and putting them in parallel is the aluminum film, which forms the Schottky contact at the N plus material, and the aluminum film forms an ohmic contact with the P plus and the N plus material. The result, as I've already indicated, is a Schottky diode in parallel with PN junction diode. The PN junction diode conducts if the structure is designed for high voltage, high current applications, but in low voltage applications the PN junction does not conduct, and we'll talk more about this in a moment. Going to the next slide, first I want to talk about reverse bias operation of the JBS diode. Here I show the diode under reverse bias conditions and a depletion region which is large enough to have formed a continuous PN junction, depletion region, which not only blocks conduction of the PN junction but also blocks conduction of the Schottky diode. And I show here the growth of the depletion region, which started from the very close to the P plus N region and has grown laterally and met with the adjacent one going from the next P plus region. The lateral growth results in a merger of these depletion regions, as I've shown, and results then in a continuous depletion region layer for both the PN junction and Schottky junctions. This depletion layer shields the Schottky junction from the reverse bias voltage, and as a result it prevents the large reverse currents compared to PN junctions that are typical of Schottky junctions. There are two principal applications of this JBS diode structure: low on-state voltages for very low voltage applications, and high breakdown, higher current applications. First, going to the low voltage JBS diode. In forward bias, we forward bias first the Schottky junction, and in some cases that forward drop can be as low as about 1/4 of a volt. far too small to forward bias the P plus N region. And the expected large leakage currents that would result under reverse bias conditions is shielded by the p-n junction depletion region that I've already talked about. The current flow is entirely by majority carriers, and there is no conductivity modulation because we do not have sufficient current to develop a forward voltage of 0.7 of a volt across the P plus N region. We have fairly narrow, widely spaced P plus diffusions here, so that the majority of the lateral area is Schottky Diodes, so that we minimize the on-state resistance of the N region. The drift region is more heavily doped to minimize ohmic drops in the Schottky channels. And as I said before, the p-n junction drop is not sufficient for turning on the p-n junction. And so this operates basically as a Schottky diode or a majority carrier device. In high voltage JBS diodes in forward bias, the lateral extent of the P regions and the Schottky regions are about the same. In other words, we've made the P plus diffusions wider than in the low voltage applications. The conductivity modulation will take place because we're going to be operating at larger currents, and there will be sufficient drop in the ohmic region of the Schottky diode channel to basically provide a 0.7 of a volt or more forward bias between the P plus and the N region, and so the p-n junction will turn on. As a result, we'll have conductivity modulation, and the excess carriers or stored charge, however, is going to be significantly smaller than a comparable PIN diode. Because of the smaller stored charge, the reverse recovery time of the JBS diode is going to be significantly faster than the standard PIN diode. The reverse bias leakage currents are going to be similar to a PIN diode because of the shielding effect of the depletion region of the p-n junctions. The smaller area of the Schottky channels and the lower doping density creates that sufficient drop to turn on those p-n junctions, and thus we'll get, as I've already indicated, the excess carrier injection into the drift region from the p-n junction. As a result, these JBS diodes can function either, if they're designed properly, at very low voltages, or they can be used at fairly high voltages. And so this particular kind of geometry for a diode is probably going to see increased usage as time goes forward. This ends the discussion of the power diodes. Thank you for your attention.